Hello everyone. This is a bit of a strange title. You hear me talk a lot. This is a YouTube channel after all, so I have to talk a lot. But why are we talking about words? I want to put it to you that there is actually quite a lot of importance of language in the context of math. Not necessarily in the way that you think, as we're going to see from a few examples, and so hopefully after this you will be willing to be a bit less lazy in the way that you write things out. We don't really call it lazy if it is irrelevant, but if it's relevant and you don't do it, then that makes you lazy. So hopefully you'll see after this that words do matter. Now, first thing, just to get this out of the way, is that I don't mean words because your school or your teacher or I told you you must use certain words. There are some conventions. For example, similar and congruent triangles have been denoted differently by pretty much everyone that I've asked. Now, for me, I use these to represent similar and congruent. I've been told that in some schools, you have to use this as similar and this as congruent. I've been told in some other schools, you are not even allowed to use any symbol for similar. You're just supposed to spell out similar, and then they say congruent, you can use this one. Okay, this is not what I'm referring to. So in any competition, be it, let's say, the SMO round 2, be it the USAMO, the IMO for that matter, nobody is going to deduct your marks or to question you because your symbol is not the same as theirs in these sorts of situations. I don't really care about this, but I had to mention this at some point because it is not being pedantic. Now, the first aspect is just the literally read things carefully so that you don't lose marks in the Olympiad aspect. Now, that is undoubtedly important. It is not terribly exciting, but that is the reason why things often go wrong, because it is not very exciting to talk about reading things carefully. This is a classic example from the junior round 1. If you are asked to find the maximum of this, and then you look at this equation, you say, I will just take the 3y squared, substitute it into here, and so you will end up with this, and then you complete the square. This is all very traditional stuff. And eventually you end up with 81 over 4 minus 4 times of this square. And so therefore you conclude that the maximum value is 81 over 4. Is that right? Some of you are thinking that that can't be right because the SMO doesn't have non-integer answers, in which case, well, in the SMO in 2015, question 10 was still a multiple choice. I just didn't include the multiple choice options here. So you can't say that non-integer is the reason for it to be wrong. But you would be right to say that I wouldn't include this example if something fishy was not there. What happens if you actually take 81 over 4 and put it back into the initial equation, or equivalently put it into here? You're going to find that y is negative. And I don't mean put 81 over 4 in, I mean that this happens when x equals to 9 over 4, and so if you try to put in that, it does not agree with that. X and Y are real numbers is not as redundant as you think it is. We're going to say more about the real number issue later. I'll leave it again as an exercise for you to tell me what is the resolution to this problem. Right, so 9 over 4 doesn't work. What does work in that case? I'm going to move on to a related point, so I'll leave this to you. I don't know why it's doing that. So, equation solving, one of the bugbears that I have is that everyone just uses commas very lazily. I have a very simple example here that is not going to cause too much of a problem, but I just want you to think about those commas and even the word or a bit more carefully. Now, in both of these situations, what you are likely to do is that you are going to say that, oh, this means that this is going to be 2x minus 3. This is absolute value of 2x minus 3. Both times you're probably going to give me something like x plus 1 equals to 2x minus 3, or negative x plus 1 equals to 2x minus 3. And I am very sure that we can just safely say most of you will write the same thing for the other one as well. Now, what is the difference between this or and that or? You see, in the English language, when we say the word or, there are two different situations that can come about when you say or. It could be a or B, meaning that they may work. A or B can also mean they will work. For example, if let's say that you brought a set of keys, right? You have got 2 keys in your hand. Now I say that, oh, either the first or second key should be able to open the door. Now that's a may work, right? So it's not the first key or the second key are both fine. It's that the first key could work or the second key could work. Now when I say A or B will work, means that I have given you 2 identical keys. So I say if you use the first key or the second key, they will work, as in that they will both be fine. There is a distinction here in the fact that for the case on the left, this modulus x plus 1 is equal to either x plus 1 or negative x plus 1. That is true. But these or are not going to be guaranteed solutions. Whereas that this or would be guaranteed solutions. So it's guaranteed will work, and these ones for me, they may work. Now another way of understanding this is actually a more mathematical way of putting it, is that this is an if and only if, this is not an if and only if. When doing algebra, it is important to actually know when you write things like this, you just put this, comma this, or this, or this. Am I actually doing both of them must work, and so therefore I get 2 solutions? Or are they both of them could work and these are candidates? So on the left side, what you have are candidates. What you have on the right side are guaranteed to work. In other words, they are solutions. Now, of course, both of these are going to give you the same pair of things. It will be x equals to 4, or, that word again, or x is 2/3. You will see that for the right case, both of these are fine. On the left, 2/3 is not fine. And it's important to know this because every time when you're told, oh, just check back and see whether it works for algebra, that's not always as feasible as one might think. And so you need to be very mindful whenever you're doing your algebra steps. When you say, oh, this, then you just write a list of steps. Sometimes you just say this. Sometimes it's not even a matter of the word or, it's just a matter of you just wrote a bunch of workings without thinking very carefully about how the steps relate to each other. Is it this implies this implies this, or it implies each other? This is perhaps going a step far for a question like this, but I want to use the simplest possible example to bring that idea across. The third thing I want to mention is this greater than or equal to sign. Now, this is a very common thing that will cause confusion. Let's say that you are doing this question where you have x plus 2 over x plus 4 and you want the minimum value. Many of you know the AMGM inequality. You will say that, oh, this means that the average, the arithmetic mean, is greater than or equal to the geometric mean. The geometric mean here is 2, and so therefore you will conclude that x plus 2 over x plus 4 is greater than or equals to 6. Out comes that word or again. Greater than or equal to. Does the symbol here mean that it can be equal to 6? Now, you see, equality holds for AMGM when these stuff are the same. Can that happen? Of course not, right? X is 4, then 2 over x will not be 4. Does that mean that this statement here is wrong because it said greater than or equal to? The answer is there is nothing wrong. But the greater than or equal to sign does not mean that it can be equal to. It just means that literally, for any x, the left hand side is greater than the right hand side, or the left hand side is equal to the right hand side. It does not mean that at any point in time they guarantee you that the left hand side will be equal to the right hand side. Instead, what we're supposed to be doing for this would be to just use AMGM on the first two things and just ignore the 4, since after all, 4 is 4. So use AMGM on two things and you will end up with 2 square root 2 plus 4. Now, I concluded that this is greater than or equals to 2 square root 2 plus 4. Once more, we have to still check whether they can be equal. But this time they don't have to be equal to 4 because 4 has just been sitting happily on the outside minding its own business. So x is square root 2. A simple way of putting this is just that I can say that also that this thing is greater than 0. I can also say it's greater than or equal to 0. Mathematically speaking, I can say it's greater than or equals to 0. That does not mean that it is possible to be equal. So this is a proving thing. Always make sure that what you claim can be attainable. But this is also just a warning when we use our symbols here. Like a lot of times you will say that, oh, so therefore this is greater than or equal to, and we want to say that in a sense it can be equal to 6. Or do we want to say in the sense that I just know that it's more than 6? I am not telling you that it can be equal to 6. Make sure that you understand that in your own mind and also convey that clearly in your solution. Because if I just stopped at this and I didn't explain this, I have not answered the question. Now on to something that is a bit more subtle. What exactly can we conclude from this statement that fx squared equals to x squared for all x? Here fx is a function. I assume that very immediately most of you will be like, okay, I cannot forget the minus. So you will tell me that fx is equal to x or fx is equal to minus x. Is this correct? The answer is that it is correct depending on what you actually mean when you write this statement. Fx equals to x or fx equals to minus x for all x has two possible meanings. Tell me which one's correct. Is it that fx equals to x for all x, or fx equals to minus x for all x? Or is it fx equals to x or fx equals to negative x for all x? We don't really put parentheses in math statements very often. We don't put parentheses in English sentences, right? But they definitely occupy a place. Programmers among you guys know that it is very important to put your brackets in the correct place. Now, the correct answer is that this is the statement, not this. And that's because this is essentially saying this. We are essentially saying that fx is identically x or fx is identically negative x for all x, means that you're telling me that there are two possible functions. This is telling me that there are two possible values for each x. Now, these are not saying the same thing, because there are more than two functions that can satisfy this. For example, fx can be the absolute value function. But even more like exotic, you can do something that is sort of like your Dirichlet function, something to the effect of fx is equal to x if x is rational and negative x otherwise. You can do something like this. And so be very careful when we say something, oh, this equals to this or this equals to that. Words matter, so be very clear. The best way you can probably specify this is that fx is in the set x or negative x for all x. This is probably the most precise way to put it. And precision is very important. I call this the importance of words. If you don't want to use words, it's fine, you can use symbols. But precision of symbols. Because symbols also depend on the definition. I think some of you have seen before this question, if you have learned complex numbers, what is I to the power of I? This is sort of like fun question that's asked, and I can sort of give you an answer, right? Because if you remember that e to the I pi is -1 and e to the I pi over 2 is equal to I, right? These are pretty standard things. So I could say then that I to the power of I is e to the I pi over 2 to the power of I. I use my exponential rule, and so I squared is -1, so I to the power of I is e to the negative pi over 2. That's pretty cool, right? hang on a second. We know that e to the I pi over 2 is I. We also know that by the definition of the exponential function, we know that e to the 2i pi is actually equals to 1, right? So which means that I can multiply them together. I can essentially go an extra loop and now say that e to the 5i pi over 2 is equal to I. And say that therefore, I to the I is also equal to e to the 5i pi over 2 to the power of I, which means that it is equal to e to the negative 5 pi over 2. I can even then say that it is also equal to, these are also I, and so by the same logic, it would also be equal to e to the negative 9 pi over 2, e to the negative 13 pi over 2, and I can even go backwards and now say that it is also going to be equal to e to the 3 pi over 2. What's going on here? Why is it like that? Unfortunately, the answer is not so simple. The answer is just literally to ask back the question, well, what is it? In the sense of what do you want this to mean? So what is I to the I means that your question that you want to ask is, what does exponentiation even mean? And so this is a fundamental question. Whenever you do anything in math, make sure you know actually what they mean, because those rules have constraints. You'll see that the same thing happens for ln. The same thing happens for roots in complex numbers. Definitions matter, and so words matter, because you need to tell me exactly what you are trying to say. Right? So it's just a little bit of stream of consciousness for me, but I hope that this just gives you the idea of why we need to be more careful when doing math than what we expect. Thanks for watching, and stay tuned for some more SMO focused videos coming up in the next few weeks.